Hello, and welcome to our podcast where we dive deep into the lives and the minds of leading scientists from around the world. I'm your host, Aizhan, and today I am absolutely delighted to be joined by Professor Alexei Mailybayev, a prominent researcher in fluid dynamics and applied mathematics from IMPA in Rio de Janeiro, Brazil. Professor Mailybayev is known internationally for his work in nonlinear dynamics, turbulence, bifurcation theory, and the first chair of the Brazilian chapter of Interpor, the International Society for Porous Media. Professor Mailybayev, welcome to Kazakhstan. It's such a pleasure to have you here at the 15th ISAC Congress in Astana.
Hello, and thank you very much for the invitation. It's also my great pleasure to come here.
Thank you. Let's start from the beginning. You are originally from Russia, and now you are in Brazil, doing cutting-edge research. Can you tell us a little about that journey? How did you get into math, and how did life bring you all the way to Rio?
Well, first of all, I'm originally from Soviet Union, if we're precise. So my father was born in Kazakhstan, in Kokshetau. I think in Kazakh, Kokshetau. And my mother was born in Vilnius. So they just met because they was both studying in Leningrad University in physical faculty, and that's how I appeared. I was born in Vilnius, but then my parents started to work in Moscow region. There is a very strong scientific center which is called Chernogolovka, a small city, but essentially it's a scientific center. And there I started to like mathematics. I think it was spontaneous, so I just certain moment I started to like it very much. I don't think there was a big pressure. At the same time, every second person in the city was scientist, so probably it's not so strange. And last 2 years of school I spent in Kolmogorov School. This is a school for mathematics and physics from Moscow University. Well, and then I studied in Moscow University, did what's called PhD in Moscow University, and then even got this degree of Doctor of Science, which I think it's not anymore in Kazakhstan, because it's in the Russian tradition there is a candidate and doctor, 2 degrees, and I worked in Moscow University in Institute of Mechanics until I changed to Brazil.
Very good, thank you. Your research touches on highly complex topics, turbulence, singularities, nonlinear dynamics. These topics can feel abstract to many. How would you explain the beauty or excitement of this kind of research to a broader audience?
Well, those what I'm working in is somehow mathematical side of the phenomenon of turbulence. And though everybody knows that turbulence is when the plane is shaking, right? So this is probably the only moment you normally hear it in your usual life. On the other hand, this is turbulence is just a non-regular motion of liquid or gas. So air is turbulent. Air is turbulent. For example, here in the room, just was person. Any person is walking. Air is turbulent behind him. Air is turbulent around the moving car, plane, and the same thing in the ocean. So when the boat moves behind the water is turbulent, and turbulence is what drives the change of the weather, change of the climate, all these forces that you experience when you drive a car and go on a plane. So actually turbulence is everywhere, and we feel it everywhere. You just don't see it because it's transparent. You don't see the motion of air, you don't see the motion of water, just simply because it's transparent. At the moment you put something in water, you start to see it. But actually the problem is that it's very complex. It's it's complex at many scales. There is some big motions, smaller motions. For example, when you think about the motion of the air around the building, so there is a motion, vortices of size of 100 meters, and 10 meters, 1 meter, all the way to 1 millimeter. It turned out that they're all connected, and connected in very complex mathematical way. And this complexity is such a big that until now the turbulence is not an explained phenomenon. So we don't know how to theoretically describe turbulence. So the theory is not that we know, but some questions are still open. No, it's in the very core of this phenomena. It is unknown, both on physical side and in mathematical side. And you was right to say that it's very complex. So it's very complex. It's an intersection of many different mathematical theories, physical theories, and it's still I wouldn't say it's clear which theory we should use in order to explain it. So that's very fascinating area. Fascinating on one side. On another side, it's threatening because it's so many years. Well, it's more than a century that the subject is very actively studied because it's extremely important. But there is no series yet. So when you enter in this subject, you already get this message. So that people already were studying for 100 years, and results still. The final goal is still could be far away.
Okay. Now let's talk about Brazil. Many people may not realize how strong the Brazilian mathematical community is, especially at IMPA. What is it like working at such a world-renowned institute? And what's unique about this Brazil's mathematical culture?
Yes, so I'm working in this institute which is called IMPA. It's not very big institute. It's probably has something around 50 permanent professors. It's a research institute. So we mainly do main goal is do research, and also we have postgraduate programs. So we have master student, less master student, and more PhD students. That's certainly one of the central centers for mathematical study, if probably the key center in South America. On the other hand, it's absolutely amusing place. So if I invite you to come whenever you will be able, and when you come, you're fascinated because it's a institute which is in the middle of the city. At the same time, it's in the middle of the jungle. So you're surrounded by tropical forest with monkeys, with tucanos flying, and it's also very, very well organized. So the organization is something exceptional. So this is kind of organization that was built in order to remove all the unnecessary activity from a scientist. So all this process, because we're not only doing science, you have to apply for the project, you have to write reports. So all this part is put in a form which is maximally convenient. So you're really free to do science. Also, there is not many requirements. So you are not forced to like in some centers, it's not obligatory to publish papers so you're really free to in what you're doing. On the other hand, it's very hard to enter, so the competition is very strong. So we usually have, when the position is opened, we normally have more than 100 applications. That's kind of a very convenient environment for doing science if you want to do the science in a calm way and really to concentrate on your problem.
Okay. You helped found the Brazilian chapter of Interpor and served as its first chair. What motivated you to initiate this community, and what role do porous media and society level collaboration play in your research vision?
Well, so this happened somewhat 10 years ago, maybe, when I was working on in the field of nonlinear waves in porous medium. So in the usual language, this is a study of how liquids and gases propagate through sand, in simple ways. And there are various applications. For Brazil, maybe the central question is oil production. So in order to produce oil, oil is under in the earth under you. So it's not, you can make a hole and oil start to come, but it doesn't come for long because there is gravity. So oil will like to stay there than to come out. So that means that you have to do another hole and inject water or something else, which will push oil through the first hole. And this is a very complicated process, physically, mathematically, geologically, and so on. And there is a whole science which studying this. And Interpor is a society, very, very big now. It's huge society which gathers researchers which are working around this porous media. Different studies related to porous media, where certainly the geophysical studies play one of the crucial roles. And they were expanding. They wanted to have local chapters. Local chapter means that kind of the part of the society which is concentrated on a specific country. And at that time they approached me asking if I can start this activity. So it was very interesting. So we opened a chapter. Made several meetings. I think one of the main activity was organizing the national events, national conferences. So we did this. We started with a smaller conference. So now it's becoming quite large. Well, at that moment, I passed this pleasure to organize the chapter to further colleagues, and so now I'm not really much involved, except that I'm participating as a member of the committee, and also I slightly changed the topic. So now working with the turbulence, we started to get new results which required really mathematical tools to develop, and so I'm almost don't work with porous media anymore.
Yeah, I read one of the recent focuses involves blow-up phenomena in turbulent flows, a topic that sounds both mathematically rich and physically meaningful. Could you tell us about that?
About blow-up in fluid dynamics. So the blow-up is... what means blow-up? Blow-up, there are equations of motion. So physicists wrote equations of motion for fluid dynamics long time ago. So the motion of ideal fluid, it goes back, equations for the ideal fluid goes back to Euler. So I think it should be like 260 years ago. And then the equation were improved and then became Navier-Stokes equation. So this is, I think, 1.5 century ago. Equations are known for a long time. We know that they, from physical point of view, they're very reliable. So really, you can use them for predicting the flow of fluid. And from mathematical point of view, there is first question you ask if you can solve them, if at least not even solve them to find a solution, but where the solution exists. So whenever you have a question, the first question, if the solution exists. Mathematical language means if the problem is well posed, if the solution exists, if it's unique, because if you have several solutions, you don't know which one to choose. So it should be unique, and so on. And it turns out that despite the problems are so old, all these questions are completely open. So blow up means, blow up is a situation when the solution exists initially, but then something happens. Something becomes infinite. So you can start solving equations. So it means that you start from some initial state of the flow, and you can predict the motion of the flow until a certain time. But then something happens with the solution. So something becomes normally derivative become infinite. Something it's called blow up. Blow up means that you cannot anymore extend the solution on the mathematical formulation that you started with. And this is a big problem. So if there is a blow up, means that you have to reformulate the change the mathematical formulation. So the problem with fluid dynamics is even this question is not known. Even the question if we can solve it for a long time or there will be blow up infinite time, it's absolutely open. For Navier-Stokes, this is quoted as one of the seven millennium problems for the 21st century. So mathematicians consider it very important. And for Euler equations, and so telling about these seven problems, they also give a prize for the $1 million. It's probably not such a big prize, depending on comparing to what. No? But anyway, so this is considered to be a very important problem for mathematics. And now for Euler equations for ideal fluid, it's probably even more important because, both questions, if whatever way they're answered, yes or no, they certainly will influence a lot both mathematical theory and physical theory of the phenomena. And they certainly important for developing the theory of turbulence. So you see that the questions of turbulence are so open that we still don't even know how to answer very, very basic questions from which you start any study in mathematics.
Yeah. You know what's funny? I think people imagine mathematicians just sitting in dark rooms doing calculations, but your work feels really alive, like it connects to nature and real world things. Switching gears a little, how do you relax? Like outside of math, do you take your equations like? Do you solve your math problems outside of the campus, something like that?
Well, these are two questions, right? So one question, how do you relax, means that what you do beyond mathematics. Yeah. Another is if you combine it with mathematics. Yeah. So that both are interesting. So certainly the usual property of the scientist is that it's hard to stop thinking, right? So usually we are trained from the school that you always think, and this is becoming almost kind of obsession. So you have to find something which forces you not to think. I had a very good type of activity that so I was climbing in the past. So it was rock climbing, ice climbing, alpinism. So that's really activity that helps you a lot, because going to the expedition to mountains, you can really find 2-3 weeks when you don't think about mathematics or physics at all. Recently, I stopped doing really the climbing part. I still hiking. I started to swim. In Rio de Janeiro we have sea, so I'm just swimming a couple of kilometers, and that helps also a lot. Hiking, I think I started to play piano. It also helps. So certainly it's very important how you relax. And the same actually helps a lot for solving complicated questions. So usually most of the time what you do is you really sit in your office. So I don't like to sit in the office. You sit. I like to sit in sofa somewhere in corridor or walking, and kind of developing make a routine scientific developments. But the central is to have an idea, because once, twice a year you need some good idea which kind of shapes what you're doing for the next half of the year. And getting idea is difficult because it's suffering. Usually when I feel that I'm not suffer, it means that I'm not getting good idea. So usually ideas come with a suffer. And one of the ways I like, so if I have some complicated question which just doesn't develop, I usually go to walk. I'm usually hiking. And IMPA is perfect for this, because just in front of IMPA we have a trail which goes through the jungle to the top of the Corcovado mountain with a Christ, It's not every time I go to Christ, but because there are many hikes with waterfalls and so on, so I usually do like couple of hours hike up to the mountains. You go to some place, sit, think, and I learned that this works perfectly. So it's almost never that I'm not. It's always I'm getting some idea what to do. Probably not every time brilliant idea, but I coming back I know what I will do. So my hypothesis is it has to do with the blood circulation. Probably when I hike like 400-500 meters up, you have more blood circulation in your body. You sit and you have a much more clear thinking state, and I recommend it to many, and I think many scientists know this. So I met many of my colleagues. Just if they want to think, they go to walk.
Yeah. I love that. I think it's so important for students and the young researchers to see that professors are real people. What advice would you give to someone struggling in their studies or feeling like lost in math?
Well, struggling is a good sign. So I think that if you study some subject and you're not struggling, that this subject is not right. You are not learning, because it means that it's too easy. So when you study the new course, struggling and suffering is, at least in my experience, tells that this is very good sign. It means that you are learning something new, because your mind is trying to resist to the novel thing. Learning new theory is it requires a lot of energy, so your brain resists. So what I can say that certainly mathematics is and in general the science. So the science and probably the art are the most complex type of activity that we do. They're abstract. Not many people do them, and they're difficult. They're certainly very much rewarding. So you have a lot of happiness. You can get a lot of happiness doing them, but at the same time they're very hard. So you need a lot of energy to put in order to get a result. So certainly, if you suffer and love it, you're in a good way. If you suffer and hate it, you probably should not do it. So that's essentially so it's not a suffering or complication that defines, but rather your feelings. So if you feel that you're happy, despite it's difficult, you should continue. It's just you can think of sport. People running marathon, but they're happy. It's difficult, but they're happy. Other people don't run marathon because then they hate it, so they should not go to run marathon. Right? So that's
Okay. Lately everyone's talking about AI, like machine learning, just ChatGPT, all that. And I keep wondering, is AI going to help with math research, or is it more hype than help?
No, it is not only going to, it does help. Well, I'm not telling about obvious, like writing reports, for example, right? But there are even very recent studies exactly on the problem of blow up that you mentioned.
Yeah.
So where the I guess it's still not finished, but it's what I understand. They almost have a proof of blow up in certain situation with what's called computer assistant proof. Computer assistant proof is a proof, so it's a mathematical proof, but simply which involves computations which can be done exactly by a computer. Simply our human limitation, we're limited. We cannot, like if you need to add two numbers, you cannot add it million of times. You just don't have time for this. But computer does it in a fraction of a second. So you can form a proof in such a way that computer does part of the job. He does it exactly. You know that it is rigorous. And this part, it's becoming clear that this part can be done by artificial intelligence. And so artificial intelligence really comes not only in helping of doing routine works, but helping in really doing non-trivial mathematical proofs nowadays. And that's a very interesting direction.
Professor Mailybayev, thank you so much for this fascinating conversation. Your work not only pushes the boundaries of our understanding of fluid mechanics and dynamical systems, but also inspires the next generation of scientists to pursue complexity with curiosity and courage. To our listeners, if you would like to learn more about our Professor Mailybayev's work, you can visit his webpage. And stay tuned for more conversations with remarkable minds in science.
Thank you very much.